Let's turn our attention now to the chaos game. You'll remember that you played this game last week in recitation, and now we're going to look at it again and try to figure out what it is you were doing as you were playing this game. Let's remember roughly how it goes. It uses a coin and a calculator. Over there on the right, I'm repeating the instructions that you were following last week. I won't go through them in entire detail, but I'll remind you, you started with a number between 0 and 1, and then flipping your coin and following instructions. You were getting to a new number and then a new number. You were calculating a whole sequence of numbers, and after having flipped the coin 5 times, then you recorded the last number you got to. And you recorded your number in a table. And then you did that same thing all over again. So again, you started with the number between 0 and 1, and you followed this recipe, and you recorded the final number at the end of your recipe, and did this whole thing several times. And your partners also did this, and you have recorded data from both yourself and your partners. Now, each time you play the game, you generate a sequence of numbers. The chaos game is an example of what we're going to call a dynamical system. That is to say, it prescribes a set of rules for generating a sequence of numbers or points. My slide says of numbers of points. It should really say of numbers or points. Sorry about that typo. And this particular game that we played, the chaos game, involves an element of randomness, right? We tossed the coin, and sometimes we got heads, sometimes tails. It was unpredictable. For that reason, this dynamical system is called a random dynamical system, or maybe a stochastic dynamical system. You also can have dynamical systems that don't have this random element. That is to say, they just tell you what to do, and there are no choices to be made depending on a coin toss. Those are called deterministic. So we have random dynamical systems and deterministic dynamical systems. Now, I likewise played the chaos game, and one of my rounds is recorded over to the right. You might want to note that I asked you to flip your coin only 5 times, but I flipped my coin 20 times. So I started with the number at the top, and depending on whether I had a tails or a heads, I followed the instructions just as you did. And I took 20 steps before I finally stopped, and I said, there's the number I got, and I recorded that value. Now, when I say I flipped a coin 20 times, I didn't really flip a coin 20 times. I actually simulated the flipping of a coin using a spreadsheet, which made it a lot faster. I didn't actually have to pull a coin out of my pocket and toss it into the air 20 times. Using the spreadsheet, I could do the very same thing. That is to say, it's as if I had done 20 coin tosses. Also, because it was so easy for me to do this so repetitively, I carried out this whole process for 70 rounds. That is to say, I followed the procedure over in the right 70 times. Picked some initial value, flipped the coin 20 times, and then recorded the result at the end. The very first one that I got is this 0.9669, etc., which you see over on the right as the last number, and also you see it in my list of results as the very first result. Following that, I'm showing you some of my other results. Now, I did that 70 times, so I generated 70 numbers in this way. And here I'm showing you the result. Each one of the numbers that I came up with, each one of those 70 numbers, was somewhere between 0 and 1, and here I'm showing you where they came up. Now, I want to look at this and see if there's anything interesting to be seen. And yeah, I hope you look at that and say, that doesn't look like it's a randomly generated sequence in the sense that it's sort of evenly spread all the way from 0 to 1. In fact, there's a huge glaring hole in the middle. And then if you look more carefully, you say, well, there's some other holes too. In addition to the hole in the middle, I see that in the middle of the piece on the left, sound familiar? I'm seeing a hole. And in the middle of the piece on the right, I'm also seeing a hole. So let me go on to the next slide. And to repeat some of what I just said, all of my results were between 0 and 1, but they weren't evenly distributed. There's a huge gap in the middle, and then there are these smaller gaps at the left and at the right. If you look even more closely, you might say, I can see some other gaps too, right? Well, you're beginning to see what this is. You probably have already guessed. that I'm going to say that we're describing the Cantor set. So why are we getting the Cantor set out of this game? Well, here's what's happening. As you flip the coin, it's as if you're generating a sequence of L's and R's. Heads means L, tails means R. No matter where you start, the first coin flip will put you not necessarily in the Cantor set, but it will put you into stage 1 of the construction of the Cantor set. That is to say, after the first coin flip, you will either have a number between 0 and 1/3 or a number between 2/3 and 1. You will not have a number between 1/3 and 2/3. It just can't happen when you use our rules. The second coin flip puts you somewhere in stage 2 of the Cantor set. So now it's not just that you're in the left piece or the right piece of the Cantor set, you're somewhere within one of those 4 subpieces. You're either in LL, LR, RL, or RR, which are the 4 possible pieces in the second stage. And on and on and on. As you are coin flipping, you're generating L's and R's, and they're telling you where in stages of the Cantor set you're going to be. So you're actually building up an address. However, what may obscure this slightly, make it not quite so easy to see, is that this new symbol goes at the beginning of the address. So in this example I've given you here, where it was a head, a tails, and a tails, the first 3 addresses that you're generating are first of all L, to tell you you're on the left piece, and then RL, right? The R going before the L, to tell you you're in the piece RL, and then RRL, which is counting from left to right, the 7th of the 8 pieces. So what this sequence of numbers is doing is it's not homing in or coming towards any particular number in the Cantor set. It's just getting closer and closer to the Cantor set as a whole. And so here's what we say. We say that the Cantor set is a strange attractor for the chaos game. No matter how you play this game, you find yourself coming closer and closer and closer to the Cantor set every time you flip your coin. Now, let me say what's in the book. If you go look in the book for the chaos game, it won't look like what I was just describing, and that's because the version of the chaos game that you played in recitation and that we've just analyzed is a one-dimensional game. The textbook is describing a two-dimensional game. It's played on a triangle, and in this game, rather than use a coin, which has only 2 sides, you roll a die, and that effectively gives you 3 options. So depending on what you roll, you move either towards corner A or corner B or corner C. Start wherever you like, but depending on your roll, you move half the distance to vertex A or half the distance to vertex B or half the distance to vertex C. This is a figure taken from the book, as it says in the caption, always move from the previous position toward the chosen vertex and then stop halfway. Now, what will you get if you play this game? Well, in a very similar way to getting the Cantor set in the other game, the one-dimensional game, here you're getting the Sierpinski gasket. That is to say, as you play this game, you find yourself getting closer and closer and closer to being in the Sierpinski gasket. We say that the Sierpinski gasket is the strange attractor for the two-dimensional chaos game.